artificial intelligence. It's really not that futuristic promise anymore, is it?
Yeah.
It's here. I mean, it's solving huge technical challenges. It's driving automation. It's pretty much everywhere.
It is everywhere, and AI is the engine, that's for sure.
Yeah.
But there's this major bottleneck that we keep seeing in all the source material you shared.
Right.
The core problem is that most of the infrastructure that companies already have, it just wasn't built for AI, not at scale anyway. It's like trying to run a Formula One car on a dirt road.
That is a perfect analogy. You've got this amazing software, these incredible models, but the actual hardware underneath it, all the road, the pit crew, it just can't keep up.
Exactly.
So I think our mission for this deep dive is pretty clear. We need to define what AI-ready really means for that foundation, for the infrastructure.
Because it's not just about hiring data scientists. You can't just license some software and call it a day.
Yeah.
It forces you to completely rethink that underlying stack.
And while that stack obviously includes the platform and software, today we're really focusing on that foundation, the compute, the storage, the networking, the stuff that makes it all work.
The things that make it stable and, efficient.
Okay, so let's start by unpacking this idea that AI isn't just one thing. It's not a monolith. The sources define 3 really distinct flavors of AI workloads.
And they have such different demands.
Right. And if you don't treat them differently, you're just wasting incredible amounts of time and money.
What's so fascinating is how the resource needs just shift so dramatically between the phases. You can't just buy one stack that's good at AI. You have to tailor it.
So what's the first flavor?
The first is training. This is the big one. Building a model from scratch, feeding it these massive, massive data sets. Think of it like you're writing the entire textbook for the AI algorithm.
Okay, writing the textbook.
Yeah. And that demands just pure brute force power. You need extreme parallel compute and huge storage throughput. It's a data marathon. It can take days, sometimes weeks.
And once you've written that textbook, then you move into fine-tuning.
Exactly. You have that huge foundational model, maybe a large language model. But now you need to adapt it. You need to teach it your specific business data.
So you're making it precise for your own context.
Yeah.
Like adding your highlights and notes in the margins of that textbook.
Perfect analogy. And the demand shifts. You still need horsepower for sure, but now it's about a balance between that compute and your I/O, your input-output. You have to iterate fast. You're testing, adjusting, retesting. And if your I/O pipeline is slow there, your data scientists are just sitting around waiting. And that's where innovation just grinds to a halt.
And that brings us to the ultimate goal, right? Inferencing.
Inferencing. This is running that fine-tuned model in production. It's deployed, it's making real-time predictions, giving insights back to customers or to your internal system.
So if training was the marathon and fine-tuning was a series of sprints, what's this phase?
This is all about instantaneous delivery. The infrastructure demand just flips completely. You don't need that sustained brute force of training. You need rock-solid reliability, and, this is the critical part, extremely low latency.
Milliseconds matter.
They're everything. If a customer is waiting for a recommendation or a security system needs an alert, those insights have to be instant. Otherwise, your real-time insights are just late insights. And that's useless.
That really frames the whole challenge perfectly. You need infrastructure that can pivot between all 3 of those modes. The sources give us a kind of framework for this, what they call the AI-ready checklist.
And that checklist is really the core takeaway for you today. It breaks it down into 4 essential pillars that your infrastructure has to have to be truly AI-ready.
Okay, what are they?
First, you need specialized accelerators for the actual AI math. Second, you need fast memory and a fast network fabric. Third, smart, efficient data pipelines. And fourth, secure and governed operations, what we call MLOps.
Let's dive into that first one. Specialized compute. I mean, for decades, the CPU is just the undisputed king of the data center. AI seems to have shattered that.
It completely has. The core insight here is that compute is not one size fits all anymore. Not for AI. You need a mix of specialized processors, each one optimized for a very specific task. It's the only way to get efficiency and keep costs under control.
So let's break down the 4 types that the source material really emphasizes. Where do we start?
We start with the CPU. It hasn't gone anywhere. It's still essential for orchestration for data pre- and post-processing. And it's still perfect for running those lightweight models. It's sort of the conductor of the whole orchestra.
Okay, so the conductor. What are the heavy lifters?
That would be the GPUs, the graphical processing units. They deliver that massive parallelism that's so crucial for deep learning, for those huge initial training jobs. They're built to do millions of tiny calculations all at the same time.
And then things get even more specialized.
Right. Third, you have NPUs, or custom ASICs. NTU is a neural processing unit. These chips are engineered for one thing, really: super efficient, low-power inferencing at scale.
So that's for the production phase.
Exactly. If you're running, say, real-time image recognition in high volume, an NPU is often your best bet to get speed while keeping your operational costs way down.
And the fourth type, the most flexible one.
Custom accelerators like FPGAs, field programmable gate arrays. These are fantastic for really custom edge AI stuff. Streaming data where you need ultra low latency. Think of bespoke AI tasks happening right where the data is captured.
You keep mentioning efficiency, which brings us to something the sources called a key technical nugget, and that's low precision math. Now, hang on. If we're building these incredibly complex models, why would we ever want to use low precision?
That's the perfect question. And it really is the secret ingredient for efficiency. We're talking about using formats like INT8 or FP8, maybe even INT4, instead of the traditional 32-bit floating point. The thing is, in deep learning, you have so much redundancy, so many parameters, that dropping the precision from, say, 32 bits down to 8 bits, it lets the chip process up to 4 times the amount of data in the same clock cycle.
So you're trading that absolute mathematical strictness
For a massive gain in speed and capacity.
but the model's robust enough that it doesn't actually degrade the final accuracy.
Precisely. You improve performance, you dramatically reduce the memory you need, you cut costs, all without losing functional accuracy. It's a brilliant trade-off. Every modern AI chip leverages this.
That's a fundamental shift. Okay, so
It's
from the processing brain, let's move to the circulatory system, the network fabric. If AI is all about moving massive data, the network has to keep up.
This is where so many organizations stumble. They spend a fortune on GPUs, but if the network is slow, those incredibly expensive processors are just sitting there, idle.
Wasted compute.
It's the most expensive kind of waste. I heard a great analogy for it. It's like paying a top surgeon an enormous hourly rate, but then you make them wait for 30 minutes between every single task because the support staff, the network, is too slow bringing them supplies.
Well, okay, that really puts it in perspective.
Yeah.
So what are the actual requirements? What's the standard for an AI-ready network?
You need 3 things. First, just raw high bandwidth. We're talking 100 gigabit Ethernet or faster. Anything less is an instant bottleneck.
Right.
Second, low latency and predictability. The data has to get from storage to the accelerator quickly and consistently. You have to keep those chips busy.
And the third.
A non-locking design. This is huge. You can't have one massive training job, something running for weeks, choking the network for all the little fast inferencing jobs that are running in production. The fabric has to let all the data flow freely without interference.
That brings us perfectly to the source of all that traffic, the data. The sources say AI is only as powerful as the data pipeline that feeds it.
It all comes down to that. And you can't just have one giant, super fast storage pool. No one can afford to store petabytes of historical data on the most expensive NVMe flash. You need tiers.
Which is where that food metaphor from the sources comes in. It's actually really helpful.
It's a great way to visualize it.
So let's start with the top tier, the hot tier.
The hot tier is like hot food. It's ready to eat right now. This is for your active data. Stuff you're accessing constantly. We're talking dedicated NVMe flash storage. It's expensive, yes, but it's absolutely necessary for the data sets you're using for active fine-tuning or high-volume inferencing.
Okay, then we move down to the warm tier.
The warm tier is like the food on the counter. You can heat it up quickly. This is often object storage or maybe scale-out file systems. It's for ongoing projects. Data you need ready to go soon, but not necessarily this exact second. It's a great balance of accessibility and cost.
And finally, the archive, the cold tier.
Exactly. The food in the pantry, cold and dark. This is your long-term archival storage, historical data, regulatory backups. It's the most cost-effective, but it's slower to retrieve. You need it for compliance and history, but you wouldn't run a live training job from here.
So the goal isn't just to have these tiers, it's to manage the data flow between them. So the right data is in the right place at the right time.
That's the entire game. It's about prefetching and smart tiering so the data is always ready before the model even asks for it. But the ultimate technical goal here, what the sources talk about, is zero copy streaming.
Zero copy streaming. That sounds like the holy grail. What does that mean in practice?
It means getting rid of all the unnecessary data movement. Historically, data would go from storage to the CPU's memory, then the CPU would copy it to pre-process it, Then it would copy it again to the GPU's memory.
Every copy adds latency.
And wastes CPU cycles.
Yeah.
Zero copy means the data flows directly from that storage pipeline into the specialized accelerator's memory. The CPU isn't the bottleneck anymore. It's free to just orchestrate. That is the benchmark for an efficient AI data pipeline.
That's an incredible level of efficiency. Okay, so that brings us to our final pillar. The process doesn't stop at deployment. We need that operational layer. MLOs and governance.
And this is the part that connects all this technical stuff directly back to actual business outcomes. MLOps, machine learning operations, is the framework that keeps everything secure, auditable, and running smoothly once it's in production.
So how does following this hardware checklist lead directly to, better business results?
It really hits three key metrics: cost, speed, and trust. For costs, an optimized system using these pillars, especially low precision math and zero copy, it just drastically reduces resource usage. You get more AI for every dollar you spend on hardware.
Makes sense.
For speed, faster infrastructure just accelerates the whole innovation cycle. You get new AI-powered features to market faster. That's a direct competitive advantage.
And finally, trust, which feels like it underpins everything else, especially with sensitive data.
Trust is everything. And it's built through governance that operates across all these layers. It ensures you have secure workflows, you can track data lineage, you're protecting privacy, you're maintaining compliance. It covers the whole life cycle.
Right.
Without that trust, none of the speed or the cost savings matter because the business will never fully adopt the model.
So if you get these four pillars right, the accelerators, the high-speed fabric, those smart data pipelines, and the MLOps and governance, you're not just AI ready, you're AI confident.
That's a great way to put it, AI confident. So to quickly recap for you, the listener, solving the hardware bottleneck is step one. You need that specialized compute, you need the high-speed network, you need that tiered storage, hot, warm, cold, and you have to wrap it all in governance.
This has been an incredibly clear breakdown, moving from just general ideas about AI to a really actionable checklist. But before we close, a final thought for you to explore.
The sources really hammered home this intense pressure to optimize, to use things like low-precision math, INT4, INT8, and these high-speed fabric to just crush operating costs and boost speed. Efficiency and cost are prioritized above almost everything else at that hardware layer. So this raises a crucial question for you to think about as you build these systems. In this relentless and frankly necessary drive for cost-efficient speed, how do you make sure that the governance controls the things that track data lineage and model versioning can actually keep up? How do you prevent that optimization from accidentally compromising the integrity of your data and ultimately threatening the fundamental trust in your model's output? It's a constant tension, speed versus security.